Hello, I'm Venkat Arun, and this is joint work with my advisor Hari Balakrishnan. Today we are going to be talking about Copa, which is a practical delay-based congestion control algorithm for the internet. It's been 30 years that we've been doing congestion control. Why are we still talking about it? Well, the internet is more challenging than ever. Increasing bandwidths bring three challenges with them. First, higher bandwidth delay products means that a sender must transmit more packets before it receives feedback on its actions. Second, the modern TCP competitive algorithms have a lower tolerance for non-congestive loss as bandwidth increases. And third, as bandwidth increases, flows start and stop more quickly, leading to a lot of short flows. And the short flows must coexist with large flows, for instance, from video streaming and bulk transfers. And short flows and long flows have conflicting interests. Short flows care a lot about delay, whereas long flows also care about throughput. And wireless links with their extremely variable bandwidths are also commonplace, and there is an entire line of work dedicated to congestion control for cellular networks. And simultaneously, while all this is happening, users are more and more sensitive to performance. The schemes deployed today are primarily loss-based, which are variants of compound, cubic, and TCP Reno. And we've known for a long time that these have problems. First, they're buffer filling, which means that they keep increasing their congestion window until there's a loss. Second, they interpret all loss as congestion, which means if there's loss for other reasons, they still slow down the rate. And finally, loss can be a very coarse signal. It is common on the internet today to see less than 1% of the packets being lost. And these last two problems worsen with increasing bandwidth. Proposals for delay-based congestion control algorithms have been around for a while. And these algorithms do solve the three challenges faced by loss-based algorithms. So why don't we see them being deployed today? Well, it seems that for every benefit that they have, they introduce a new challenge. Yes, because they're delay sensitive, they can maintain low delay. But this makes it challenging to be competitive with buffer filling schemes. They are robust to misleading loss because loss is not their primary signal. But delay as a signal can be misleading too. Fortunately, delay is a very rich signal, and we get multiple bits of information with every acknowledgement. However, interpreting that information is hard. For instance, to maintain low delay, it is essentially to know the true minimum RTT. And finding that is hard. Our key contribution in this work is to propose Copa, which solves these three challenges to create an algorithm for the internet that actually works. So it is difficult to be competitive with buffer filling schemes because delay-based schemes try to maintain low delay, and buffer filling schemes don't care for delay. Which means that buffer filling schemes are going to fill the buffers, and the delay-based schemes will interpret that as congestion and slow down. Our solution to this is to detect whether a buffer filler is present, and if it's present, we simply give up on having low delays because there's nothing we can do about it. Delay can be a noisy signal, and we shall show that a more robust statistic for queuing delay is to take a minimum over a large number of samples. Finding the true minimum RTT, which corresponds to the RTT when the queue is empty, is hard. And to fix that problem, we empty the queues periodically. Now, all this is fancy modern 2018 talk. What are the fundamental basic goals of congestion control? First and foremost, we must avoid congestion collapse. Second, we must allocate throughput in an efficient and fair manner. And finally, we should have low delay. Central to achieving these basic goals in our design is the definition of a target rate. Every Copa sender seeks to transmit at a rate that is inversely proportional to the queuing delay. The proportionality constant is controlled by delta, which is half by default and is controlled by an in-algorithm loop. As a side note, this target rate corresponds to each sender selfishly optimizing a utility function of the form log of the throughput minus delta times log of the delay. Here, each sender can set its own value of delta, and that controls how the sender varies the competing priorities of high throughput and low delay. When the senders do this, there is a unique and efficient Nash equilibrium. Of course, this analysis makes several assumptions, the most important of which is that the packet arrivals are Poisson. You can find more details about this in the paper. Having a target rate is very convenient because every sender knows in which direction to change its rate. However, the target rate is a function of the queuing delay, and that can be non-trivial to estimate. Let's take a look at an example. The purple part shows the true minimum RTT. This is the RTT that occurs when the queuing delay is 0. When a sender enters, it fills up the queues, and the resulting queuing delay is shown by the green part. Now, as a sender enters, it does experience the true minimum RTT, which means RTT min, which is the minimum RTT that it has ever experienced, corresponds to the true minimum RTT. This sender can correctly estimate the queuing delay as RTT minus RTT min. But consider a new sender that arrives. This never sees an empty queue, and therefore the RTT min it experiences does not correspond to the true minimum RTT. And if this sender computes its queuing delay as the RTT minus RTT min, is going to get a wrong result. The solution to this problem is to build within the mechanism a property that the queues are emptied periodically. And if this happens, any new sender will quickly see an empty queue and get the correct true minimum RTT. Is that it then? Well, the world is unfortunately quite messy. This is an example of a link from Stanford to AWS Northern California. We plot the delay experienced by each individual packet, and as you can see, it seems quite noisy. There are clearly sources of delay variation other than queuing, and this is expected. This is a cellular link, and the physical layer is going to add variable delays. So how do we decouple all these other sources of variation from queuing delay? To see that, let's go back to one of our cartoon diagrams. The purple again shows the minimum RTT, the green again shows the queuing delay, and the blue shows all the other sources of delay variation that we want to ignore. These other sources could be from wireless links, they could be from cross traffic, or ACK compression, or even just the sender transmitting packets in a bursty fashion. The key to decoupling queuing delay from these other sources is to notice that we can treat these other sources as positive additive noise. And the way we remove positive additive noise is that we take a minimum over several samples. In this case, we take a minimum over the last half RTT, which is a somewhat arbitrary choice. We go back to our example of the Stanford to AWS Northern California link. If we switch the queuing delay estimator in our algorithm from the RTT minus RTT min to the new estimator, we get an 8x improvement in throughput with hardly any increase in delay. So now we know we have a definition of a target rate. We know how to compute the target rate. However, now we need to look at how we attain that target rate. In Copa, the algorithm is quite simple. If our current rate is less than the target rate, we increase it additively, otherwise we decrease it additively. To speed up the convergence, we have a velocity parameter, which is 1 most of the time, but if the current rate is far from the target rate, it increases, and this allows for faster convergence. The resulting behavior is quite simple. Both the congestion window and the round trip time oscillate about their equilibrium values regularly. Notice that the y-axis is zoomed in and does not start from 0. Let's try to understand these oscillations analytically. In this talk, we are going to consider the case of one sender. If there are multiple senders, they behave like one sender but with a smaller delta. You can read more about that in the paper. In the one sender case, the period of the oscillations is 5 RTTs, and the amplitude is 2.5 delta inverse. There is a different way to interpret our target rate. We can interpret the target rate as saying that each sender should try to maintain 1 over delta packets in the queue at all times. If the current queue length is smaller than this, then we speed up, otherwise we slow down. Let's concentrate on the topmost point where the direction changes from increasing to decreasing. The RTT estimate that the sender has at this time instant corresponds to the packet sent 1 RTT ago. This is the feedback delay. At this point, the sender also maintains a half RTT window of samples over which it computes the minimum. Remember, this was for denoising the RTT samples. Therefore, the queue length corresponding to the RTT corresponds to the point shown by the red arrow. When this crosses the equilibrium queue length, the sender is going to switch direction from increasing to decreasing. Therefore, it switches after half plus 1, which is 1.5 RTTs, after the queue length has crossed the threshold. A similar reasoning applies in the other direction. We have adjusted the queuing delay, the slope of the increase or the decrease here, so that the queuing delay becomes 0 periodically. In this case, after 5 RTTs. This property that the queuing delay goes to 0 every 5 RTTs has two very important consequences for us. First, as we have already seen, it allows us to estimate the true minimum RTT. Second, it allows us to detect the presence of a buffer filling TCP. If the queue does not empty once every 5 RTTs, then we assume that the buffer filling TCP is present. This allows for TCP competitiveness. TCP competitiveness requires that if an existing buffer filling TCP, such as TCP cubic, is present alongside a new algorithm, such as Copa, they should share the bandwidth fairly. And this is important for any new scheme that we deploy today. Let's see how Copa fares in the presence of TCP cubic. The green line shows Copa's throughput, the blue line shows TCP cubic's throughput, and the dotted lines show the queuing delay experienced by these two flows. When only Copa flows are present, they get both high throughput and low delay. However, when a TCP cubic flow enters, it increases the delay, and Copa misinterprets this as congestion and slows down. It is possible to make Copa more throughput aggressive. We can do this by doing additive increase, multiplicative decrease on 1 over delta. 1 over delta controls how aggressive Copa is. You can find more details about this in the paper. In this graph, see that when we do this, Copa and cubic do fairly share the same buffer. However, when only Copa flows are present, Copa is now a buffer filling algorithm and attains high delays. We want the best of both worlds. And we do this by performing mode switching. We have a detector that detects the presence of TCP, a buffer filling TCP. If it's not present, we have set delta equals 0.5, get high throughput and low delay. If it is present, we give up on having low delays and we still get high throughput. How do we know whether a buffer filling TCP is present or not? Note that when only Copa flows are present, they empty the queue once every 5 RTTs. If this does not happen, we know that a buffer filling TCP is also present and we switch to TCP competitive mode. In this experiment, we test TCP competitiveness. We run cubic flows in parallel with flows of another algorithm, and we run this over a large number of randomly chosen networks with randomly chosen degree of multiplexing. When cubic flows compete with other cubic flows, they get on average 80% link utilization. However, when Copa flows compete with cubic flows still get their 80%, but Copa is able to utilize the unused bandwidth to get higher throughput. PCC and BBR get much higher throughput, but this comes at the cost of existing flows. Vegas is a delay-sensitive algorithm and loses out in the presence of TCP cubic. So this completes the description of our algorithm. Let's look at the limitations. First, note that we ignore other sources of delay variation by taking a minimum over a half RTT period. If the other sources of delay variation vary more slowly than this, then taking a minimum cannot ignore it anymore. Therefore, Copa cannot ignore low frequency noise. Second, we have this property that the queue is empty periodically. This property breaks if the propagation delay is much smaller than the queuing delay, or if flows with very different propagation delays compete on the same bottleneck queue. When this happens, Copa erroneously switches to TCP mode, but even in that mode, it still provides performance benefits over TCP cubic, which is the default in the Linux kernel, for instance. And finally, Copa requires precise RTT measurements. For instance, if Copa runs on a 10 Gbps link, it tries to maintain a queuing delay of 2 microseconds on average. If it cannot measure delay to that level of accuracy, then then COPA is not going to work anymore. One way to fix this is to reduce this constraint. Let's say we maintain 10 microseconds queuing delay, and 10 microseconds is something that we can measure. Then COPA can still work. This, however, remains part of future work. Now we look at performance on real paths. We look at the Pantheon testbed, which is a testbed for congestion control algorithms. They have links all over the world, and they periodically run flows with different congestion control algorithms on them. We have separated the links into cellular networks and wired networks. And we plot the average throughput and average delay, where the averaging is over all the runs across all the links. We see that in both types of links, COPA gets consistently high throughput and low delay. Schemes that perform well on one type of link do not perform so well on the other. In this note that Vivace LTE, Verus, and Sprout were specifically designed for cellular networks. Now we look at a satellite link, which is challenging because it has a high bandwidth delay product and a high packet loss rate. Here, both COPA and REMI, which is an automatically generated protocol, achieve high throughput and low delay. Cubic and Vegas lose out because of the high packet loss rate. And BBR gets low delay, but because of the high bandwidth delay product, its throughput oscillates a lot, which causes it to underutilize the link. PCC gets very high throughput. However, this comes at the cost of getting nearly 800 milliseconds of delay. Now we look at the performance of various schemes with inter-scheme fairness. Here flows enter one by one for the first 10 seconds, 1 second at a time, and then they leave 1 second at a time for the next 10 seconds. The black line shows the ideal fair throughput allocation, and we plot the mean plus minus the standard deviation of the throughput attained by each of the flows. Here we see that both COPA and Cubic are able to track the ideal black line quite closely. And BBR and PCC fail to do so. This is because the first flow that enters the network gets to keep a majority of the bandwidth and does not slow down for the other flows. COPA gets marginally higher fairness than Cubic because COPA is sensitive to delay, which is a much more fine-grained signal than loss, which is what Cubic depends on. So in summary, we have presented a delay-based congestion control algorithm that is practical and works well on the internet. The key ideas are as follows. There's a network, and we have a queuing delay estimator. The estimator uses two ideas. First, it ignores loss by taking a minimum over several RTT samples. And second, it computes the target rate from this queuing delay. The target rate depends on the parameter delta, which is adjusted by an outer control loop. This outer control loop detects the presence of a TCP and varies delta to make sure that it is competitive with TCP if a TCP flow is indeed present. And finally, we have a simple algorithm which is a variant of additive-increase, additive-decrease that allows COPA to move toward this target rate. This algorithm sets the rate and the congestion window, which goes back to the network. Thank you.
Questions?
Hi, nice work. David Chu, Google. So my one question that I have is, you showed how BBR is maybe less fair than COPA versus Cubic. It would seem that in a game theoretic sense, folks would like to, or individuals would like to move to BBR because it does grab a higher share. And so in that world, is COPA, if COPA were to mostly compete with BBR, is COPA going to maintain its low loss property? Could you comment about that? And then also my second question was, how would COPA do in the presence of like Wi-Fi networks with like aggressive link layer aggregation and additional phenomenon on the wireless channel? Thanks.
Thanks for the question. So for the first question, yes, if in a network people wanted to burst traffic, they always have the option of doing so. And as academics, it is our responsibility to ensure that the schemes that are deployed on the internet allow everybody to share throughput fairly. And you are right that in a world with COPA and BBR, it is in a person's selfish interest to use BBR instead of COPA. And this has existed for a while, and we have specialized TCP schemes which allow schemes to burst packets. But COPA can be made more aggressive too. So in this slide, we saw that we made COPA's aggressiveness match that of TCP by doing AIMD on 1 over delta. We can change the scheme to make it compete fairly with BBR as well. So that part is flexible. And the second question, on Wi-Fi. So for that, when there is aggressive batching, we can treat so when aggressive batching occurs, the queuing delay varies a lot. And we can treat those delay variations as loss here. And the way we ignore the loss is to take a minimum over several packets. And we actually tested links with that much aggregation, and COPA is able to ignore that and get the proper queuing delay. And we believe that this trick is more widely applicable than just COPA, taking a minimum. Thank you.
Sharif, AWS. Thank you for this work, and I have two questions actually. So the first one is, were you able to quantify the price of anarchy compared to an optimal solution that in your Copa algorithm, how far it is from optimal? And the second question is that if it's possible to use the already estimated RTT values, which is a kind of a first order filter that also filter noise in the measured RTT inside TCP flows.
So your first question is it to quantify the price of anarchy?
Yes.
So the price of anarchy, if you don't care about loss, is to simply transmit at say 2x the link rate. And then you get the entire link bandwidth and nobody else gets anything. Does that answer your question? Did I misunderstand it?
Yeah.
So a person could do that, but fortunately there's also enough isolation in the network that you won't harm too many other people because there is a lot of fair queuing inside the network. But yes, you could possibly do that. And your second question, I did not understand it.
The second question is that what is the difference in the filtering mechanism that you have compared to the estimated round trip time inside the TCP flow?
So TCP does a variant of a smoothed average to estimate the RTT, and there the purpose is to compute the timeout value. And in this case, for instance, if we do a smoothed estimate, we would get a line that's somewhere in the middle of all those dots. That still contains half of the noise that we are wanting to remove. Like half will be gone, which is above the average, and a half will still remain. What we want to do is to remove the short scale variations in time, because the queuing delay itself does not vary on a short scale, because we don't vary our rate at a scale that's faster than an RTT. And therefore, the purpose of the two estimators are different. And if we use the TCP estimator, we would underutilize the link. So it's approximately. So in this case, we'll approximately still get half a megabit per second of bandwidth in this case. So, thank you.
Victor Vasilyev of Google. How do properties of your algorithm in terms of performance and convergence vary depending on the size of the buffer on network?
Thank you. So this algorithm, since it's a delay-sensitive algorithm, is immune to buffer bloat. Because it's never going to exceed the buffer's capacity. If we have very short buffers, we have a mechanism if the loss rate is greater than 30% packet loss, then we assume that cannot be because of congestion, and we reduce our rate. And the 30% value we came up by copying your value in BBR. So that's the threshold. So in short buffers, it will reduce its rate. Thank you.
Oh, let's thank Venkat again.